All right, so it's 17 hours, so we continue. We still have quite a bit to do before we can wrap up the course, but I think we're on track. Okay, so I'm not sure if people have questions with regards to what we've covered so far in lecture series number 14. If there are no questions, then we'll continue with, hopefully we get to cover binary multiplication and binary division today. Maybe we can also set the stage for our discussion of so-called unsigned integers, because it turns out that what we have been looking at so far are unsigned integers, right? So we want to, okay?
When are we going to receive our results for the quizzes that we wrote and the test?
Yeah, for those things haven't been marked. There's no timeline. I don't know when, but hopefully before you write the exam. They have to be manually marked, and we haven't yet gotten a chance to do that. I did mention that once they are marked, email communication will be sent through, just like we do when the quizzes are marked. All right, so I was just saying, a reminder that what we've been covering so far is unsigned integers, right? So positive numbers, essentially. And we've been very careful when discussing things like subtraction of binary numbers. We've been dealing with instances where we are subtracting a smaller number from a larger number. But before we start, I thought we'll just quickly go through a few announcements. All right. Yeah, so can I ask that you mute your microphone, wherever you have your microphone on? There's a bit of echo in the background. Right, so quiz number 12, right? I thought it was very, very strange. Very, very strange that people didn't perform as well as we expected. I mean, just the previous day, I think, when we had class, I'd mentioned, right, that you guys would probably have access to calculators, right? And so, but of course, I'd hinted at the fact that you're probably better off actually doing the calculations on a piece of paper so that you familiarize yourself with the process, because like it or not, these questions are coming back in test number 2 and the final exam. But yet and still you had people that were getting zeros. I don't understand. I don't understand that you'd get a 0, right? You would get a 0 when when you literally have access to a calculator. And this actually ties into a comment I got about time, right? Oh no, the time was not enough. Well, the time was not enough because we knew that you'd have access to things that you'd use to verify the answers or the solutions. And in fact, in certain instances, or most instances, to generate the solutions. And to make it slightly more complex, it's one of the reasons why we gave you that long string, right? That 40 character long string, hexadecimal string. But yet and still people were getting, there are people that got zeros, shockingly enough. Either you've been missing classes, you're not studying, or I guess you're probably one of those people who just simply doesn't care about what's happening, right? Either way, I thought it was really sad. Good luck with that anyway. So I thought it was very strange. So what we're going to do is, I know there's an assessment which we were supposed to have revised over the weekend, but I didn't want to disturb the flow of lecture series number 14. Assuming we wrap up lecture series number 14 by, let's say, Saturday, because we have the class on Friday and on Saturday, then on Sunday, what we can do during our makeup session is we can make use of that makeup session to review quiz number 12 and number 13, for the benefit of those that are still a bit confused with what we did. But I thought it was quite strange and disappointing. And in fact, the smart ones, the ones that were getting 10s out of 10s, were probably the ones that were automatically generating these things. This quiz that you wrote was actually literally giveaway, right? Free 1 mark, except for maybe the 2 questions, the true-false questions. Maybe that would have confused some people. But really, I mean, I was shocked myself. I was shocked when I was looking at the results. I really couldn't believe what was happening here. Serious case of people not being logical enough, not being smart enough to figure out what's happening here. Anyway, at least the picture is not as bad as 11, right? Even though the vast majority of the class literally failed, so they got less than 4.5, but we had a reasonable number of individuals that performed relatively well. It's a consolation. I mean, although at this stage we were expecting that the coin would be flipped. Actually, we were expecting these 40 here to be the ones that were getting more than 4.5, not the opposite that we have. Right? I don't know. I just don't know. Right? It's really bad that we have. I mean, we have this kind of scenario here, and the 33 here are not even D pluses; these are Ds, right? You know what a D is? It's less or equal to 39, right? Anyway, percent. Very sad. The distribution, I mean, it hasn't really changed that much, and it's a very strange distribution, but again, it's not what we would have hoped for. It's not what we are hoping for. Again, I keep saying that what we are hoping for is this scenario here, right? There'll always be those outliers, so-called freaks of nature, I guess, who get really high scores here, right? And there'll be a few individuals, we always expect a few individuals who just simply don't care about the course, or perhaps you don't have the aptitude for the course, I guess, I don't know. But the vast majority of people we expect to be here, right? And this is not happening yet. Quiz number 12 of 20, not happening. Hopefully it happens soon anyway. So this is what I was talking about here, right? Why can't you be like Esther, right? Or Clarence, or Teresa, or Mr. Chisha there, right? If you have people that are getting these sort of scores, what's stopping you from getting these same marks? Could it be that Esther has something that you don't have, or Esther has access to certain information that you don't have access to? I don't think so, right? Probably, I would wager here, and I'll probably sacrifice my pinky finger here, that I'll wager that these people are reading, they're attending class, they're playing back the recorded lectures if they miss class, so that you understand what's going on. What you're writing right now, these quizzes you're writing right now, a sneak preview of what is coming in the exam. Right? This is a gentle doses of what sort of questions you should expect in the exam. Right? So if you're not performing as well right now, it's probably going to be worse in the exam, right? Because the exam, by the way, is going to be an in-classroom exam, right? There's nothing like an online exam here. You're supposed to be ferried, you're supposed to be told or instructed to come back to campus very, very soon to come and write the final exam. Right? So if you don't pull up your socks right now, this is going to be a bit of an issue here, right? Very disappointing, really. Very disappointing. I don't know. Anyway, just to remind you that we have class. Oh, these classes. We have class on Saturday and on Sunday, right? We need to catch up. I don't know if we've been caught up with the sessions that we missed, but it doesn't matter. I guess we can continue having these makeup classes so we can finish off the course in good time, so that we have at least maybe a week or so, which would be good. So we have class on Saturday and Sunday, right? Friday and then Saturday and Sunday. And then on Tuesday, we have quiz number 13. Please prepare. Quiz number 13 is going to be based on binary arithmetic, so addition, subtraction, multiplication, and division. Right? So you want to prepare for these things. And then we have, of course, makeup classes the other weekend, right? So weekend after the coming weekend. So again, like I said, we will have a revision session to discuss the last couple of quizzes we've had, so that we can try and see if we can fix this on Sunday. I think we should be done with lecture series number 14 by Saturday. So we'll use Sunday to just do a bit of revision, and then on Monday we can start with lecture series number 15, which is data encoding, is essentially. Very interesting course. I find it interesting myself. Okay, so I guess we can continue. This is really bad, right? This is really bad. I don't understand. You're online, you're writing this exam online, you have access to a calculator. Why can you not use this set of assessments to practice how to use the calculator you are going to use in the exam when verifying the answers? Why could you not do what Lighton is going to do right now, right? Calculator, boom. In fact, I know what you're thinking, well, but I don't have a computer, I have a phone. Well, go to Android and just search for advanced calculators or something, Android calculator, or is it numeral system, or I don't know, number system calculator or something. I'm sure you'll find a good enough calculator for your phone. You use it to verify this, right? But if I were you, I would just gain access to a calculator that I'm going to use in the exam so that you can already familiarize yourself with how you are going to use that thing in the final exam, which is very soon. It's next month, right? That's when we're writing the exam, I think. I don't know if we're writing in December or November or something. But here's the thing, right? Why couldn't you just do what Lighton is going to showcase right now? You're writing the quiz? I don't understand that. I was expecting 10 out of 10s here, right? Or at least at the very least 8 out of 10s or something. But instead what we're getting are zeros. People were getting zeros in this quiz. You are not studying, you're joking with this. But anyway, so why could you not do this, right? You come here and you have this question here, and there's a question, oh no, why are we doing this? Oh, you're doing this because some of you are going to be teaching this. The government is paying your way through university because they are betting on the fact that the vast majority of you are going to do what Lighton does. You teach other people these things. For you to teach other people these things, you must understand. Not only that, those of you that are going to pursue alternative career paths are going to probably end up using some of these things, right? I can effectively work with tools like Git. When I'm working with Git, I don't have to worry about coming across things that look strange. You know why? When I come here and I'm using Git, you know why I can effectively use these things here? Because I understand number systems. Now, if you've got into a stage where you still can't connect the dots, right? You can't connect the different pieces of the puzzle, and you're asking, lecture series number 14, we're almost done with the course, and you're asking, why are we doing this? Then there's something wrong with you. Anyway, so why could you not do this, right? You come to question number, I don't know if it's question number 1 or something. They're asking you convert this hexadecimal short version hash code into its equivalent binary. Copy, right? Now start counting here. 27, 28, copy, right? You just come here. This is hexadecimal. You paste, and then you say binary, right? You get the answer, copy, then you paste it. What was so hard about doing this, right? Really, I mean, seriously, what was so hard about doing this? Or at least verifying after you worked it out on a piece of paper, you verify it to make sure that what you did was the correct thing. What was so hard about doing this? Let's just continue with this. Okay, so we are going to continue our discussion of binary numbers. So we looked at binary addition, essentially just looking at the rules, and then I think the last time we met, we discussed binary subtraction, again, more rules, right? And we discovered that as opposed to binary addition, where you have these very weird rules, with subtraction, the only thing that you have to worry about is a situation where you're subtracting the 1 from the 0, right? In which case you start borrowing from the adjacent 2's places on your left, right? And remember, when you borrow, you're borrowing two of whatever one thing you borrow. So if you borrow from the 2's place to compensate for what you have on the 1's place, then what you're getting actually are 2 1s, right? Because every successive adjacent 2's place is 2 steps ahead, right? So 1, 2, 4, 8, 16, 32, 64, right? 128. So very simple rules, right? You just have to remember that when you're borrowing these things, and you remember one of the examples, actually, we stumbled a little here because when we were borrowing, we forgot the fact that we had remained with a 1 or something. I don't know if you remember that. So we are going to transition to binary multiplication, right? Which is trivial, really relatively easy. So it turns out that you can actually perform binary multiplication in more or less the same way that you perform multiplication for base 10. Remember, we're still latching on to base 10 here because we know that everybody enrolled into the course, at least, is familiar with decimal numbers or base 10, right? Multiplication, addition, subtraction, and division of base 10 comes naturally to us. We've been doing this since grade 1, right? So we're going to take advantage of the same techniques we use in base 10 to try and see if we can apply them to binary numbers. So what you do is, obviously, when you're multiplying two sets of numbers, you multiply them from right to left, right? Just like you do with decimal numbers. So if you had 20, if you had, let's say, 20 or 202 base 10 multiplied by, let's say, 12 base 10, or 10 base 10. 10 is a bit weird, right? Or let's say 11 base 10. We were told how to do this, right? We multiply the numbers right to left. So what you do is you go this way, right? So it'll be 1 times 2, 1 times 0, 1 times 2, and then you move a step, and then you multiply 1 times 2, 1 times 0, 1 times 2, and then you add the result. Now notice the addition part here, obviously latches on to what we introduce as binary addition, right? So you typically add them as you would, you follow the same rules that we followed when we're looking at binary addition. So same concept is what we're going to apply here, right? When we're multiplying binary numbers. In terms of the basic rules, more rules here coming our way. And it's quite easy because we're working with two symbols. We only have 3 possibilities. The idea was supposed to be 4 possibilities, but 1 and 0 is the same as 0 and 1. So what we're saying is 0 times 0 gives us 0, 0 times 1 gives us 0, 1 times 0 gives us 0, 1 times 1 gives us 1, right? So these are the different scenarios that we work with when multiplying binary numbers. So we'll immediately jump into an example here. Let's say we are multiplying 3 and 3, right? We're supposed to get 9 here. I don't know if you can tell it's 3, right? 1's place, 2's place. 1's place, 2's place. 2 plus 1, 2 plus 1. So it's 3 times 3, which is 9, right? So let's say we are multiplying 1, 1, and 1, 1, right? How do we go about evaluating this expression? Oh, it's simple. We start by evaluate from right to left. It will be 1. I hope the visualization is here. So it will be 1 times 1, right? We get 1. And then we'll multiply this one and the next adjacent one. We get another 1. And then we move to the next 2's place. And then we start multiplying 1 and 1. The next 1 and 1, we get 1. And then 1 and 1 gives us 1. And then we add these 2 numbers, or resulting result, these sub-results, we add them together. So addition is quite trivial here. All we do is we follow those rules, right? 1 and nothing, which is 0 here, is 1. 1 and 1 gives us 0. The remainder is 1, right? The carry bit is going to be here. So effectively, we have 1 and 1. 1 and 1 is going to give us 0. We have another carry bit. Then we just drop the carry bit because it will be 1 and 0. And then we get 1, 0, 0, 1. Now, if we're a bit strict with so-called bit representation, like if we wanted to represent the answer using 2-bit representation, we'd have what's called an overflow. And we discussed an overflow here, but essentially what we're saying here is that the answer is 1, 0, 0, 1. And it makes sense because this is 9, right? This is 1's place, 2's place, 4's place. Sorry, 1's place, 2's place, 4's place, 8's place. So 8 plus 1 is 9, right? We get 9. Is this making sense? The only part here that you have to, multiplying is trivial. Why is multiplying trivial? Because you're multiplying either 1 and 0, 0 and 0, or 1 and 1, right? What might be a bit confusing when you're starting off here is adding the numbers. Do you understand this?
Yes, sir.
Yeah.
Yes, sir.
Right, so we have our 9 there, right? Yet another example here. Sorry, is there a question?
No, finish up first, and I'll ask it.
Okay, so another example here. Let's say we are multiplying. What is this? This is 1's place, 2's place, 4's place. So this is 5, right? 1 plus 4 is 5. 1's place, 2's place, 4's place, 8's place. So 8 plus 2 is 10, right? So it's supposed to have 50. So we are multiplying 10 by 5, which is supposed to be 50, right? Yeah. So what we're saying is, what happens when you multiply this number? We're going to get 50, right? Same process. we start multiplying from right to left, right? One twos place after the other. So we start with this twos place here. So 1 and 0 gives us 0. 1 and 1 gives us 1. 1 and 0 gives us 0. 1 and 1 gives us 1. Then we move on to the next digit here, which is 0. This is trivial, it's all going to be zeros, right? Do not forget to move the next twos place here once you start evaluating the next digit on the left, right? So 0 and 0 gives us 0, 0 and 1 gives us 0, 0 and 0 gives us 0, 0 and 1 gives us 0. Then we evaluate this 1, right? We move the next digit, it will be 1 and 0 gives us 0, 1 and 1 gives us 1, 1 and 0 gives us 0, 1 and 1 gives us 1. And then we just add. Remember, this case is slightly different because we are adding 3 sub results, these things here. But again, the rules apply. The rules that we looked at for binary addition apply. Yeah. So again, to add this, it would be 0, 0, 0, 0, it would be 0, 1, 0, 0, it would be 1, 0, 0, 0, it would be 0, 1, 0, 1 is 0, remainder 1 or carry 1. 1, 0, 0 will be 1. This is a lone one, we just drop it down, it's a 1. And if you look at this, it's obviously going to give us the answer we want. Why? This is a ones place, twos place, fours place, eights place, sorry, ones place, twos place, fours place, eights place, 16th place, 32's place. So 32 plus 16 plus 2, which gives us 50. And then we have our answer. Is this kind of making sense? Or you probably...
Makes sense, sir.
Okay. Is anybody confused here before we get to binary division? Because, I mean, this is it here. But maybe, it's a thing, right? Observe, I mean, you might... We're probably just going to bring this in the quiz, but we might as well do it here. Imagine a situation where you're multiplying significantly larger value or larger numbers, because the larger the number, I don't know if you notice a pattern here, right? If you're working with let's say a smaller number like 1 1 and 1 1 1 0 something, what you notice is that the sub processes that you're adding are smaller, right? Like in this case is 2. In the next example, what we have is a kind of situation where the sub processes that we have are 3, right? 3 because the number below here is slightly larger, right, than the ones we are working with. But imagine a situation where we have, let's say we want to multiply. Let's do this. Let's multiply 50 and 10. No, 50 and sorry. Yes?
What do you mean 50?
Oh, sorry, 10.
No.
10, sorry. This is 10, sorry. And then I was thinking about the answer. Let's multiply 10 and 10 so that we get 100, right? So 10 and 10. And remember, I'm still using the decimal because I know it comes naturally for most of you guys. Or let's multiply 1010 and 1010. Let's look at what this will give us, right? Observe. And I hate using my mouse, right? Everybody's in the mouse, horrible. Let's do this using a spreadsheet, right? 1 0 1 0, right? Multiplied by 1 0 1 0. What I'm going to do is I'm just going to, you might need placeholders here. I'm just going to highlight this. Now observe, we're saying we start with the rightmost bit here, so it will be 0 0 0. Sorry, 0 0 and 0 gives us 0. 0 and 1 gives us 0. 0 and 0 gives us 0. 0 and 1 gives us 0. We come to this digit here. We move here, it will be 1 and 0 gives us 0. 1 and 1 gives us 1. 1 and 0 gives us 0. 1 and 1 gives us 1. We come to this 0. Move here. 0 and 0 gives us 0. 0 and 1 gives us 0. 0 and 0 gives us 0. 0 and 1 gives us 0. I don't know if you can see what I was trying to get at. We come to this last one here. It will be 1 and 0, it's 0. 1 and, oh, so hoping there would be such a case that we wanted. 1 and 1 gives us 1. 1 and 0 gives us 0. 1 and 1 gives us 1. Right? So what we're doing now is we have a situation where we are adding 4 sub-processes. 1, 2, 3, 4. It's the same rules though. Right? It's just that it's unfortunate here that we don't have a case that I wanted to showcase. But observe, let's switch this a little. Let's and the answer, by the way, here, let's evaluate the answer. The answer is going to be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0 is 1, 0, 0, 0, 0, 0 is 0, 1, 0, 1 is going to be 0, remainder 1, 1, 0, 0, 0, 1, and then drop the 1 here. And if we were to calculate this here, we'd get, this is, and I'm beginning to think here now, right? This is 2 to power 0, 2 to power 1, 2 to power 2, all the way up to here, right? Come on. This is not working. 2 to power 0, 2 to power 1, 2 to power 3, 2 to power 2, sorry, 2 to power 3, 2 to power 4, 2 to power 3, 0, 1, 2, 3, 2 to power 4, 2 to power 5, 2 to power 6. So effectively what we're saying is our answer is 4 plus 32 plus 4, right, which is 100, right? But observe, right? What if we switch this a little, right? We're just going to take advantage of this. We're still going to have 4 sub-processes, but we're going to switch it up a little and say, what if we come on, okay. What if we have these strange numbers here, right? We have these strange numbers where instead of multiplying 10 by 10, let's multiply, what number is this? This is
15.
0, sorry?
15.
Perfect, yes, 15. Right, it's a nibble, right? So it's 15, the maximum number. Right, so we want to get this number here, right? 225. So the question is, how do we do this if we're multiplying? Well, it's the same process, right? We start right to left, but I want to showcase a very strange thing here that might be confusing if you're ever faced with this situation. 1 and 1 is going to be 1, 1 and 1 is 1, 1 and 1 is 1, 1 and 1 is 1. We come here, we start here, 1 and 1 is 1, 1, 1, 1, right? We come here, 1, 1, 1, 1. Then finally we come here, the last one is 1, 1, 1, 1, right? I'm just going to insert a row here, then move this multiplication. Yes, I can move it here anyways. So, nah, it would be better placed at the end. So we have this situation, right? Observe the sub-processes that we have. Very strange kind of situation, right? Why is it strange? Because we have this thing here we haven't discussed yet. But I know you've already figured out how to do this, right? Yeah, we only discussed the rules only apply to three ones, right? It doesn't change a thing. What you can do is you can view this problem as being a multi-part problem, where instead of having 4 processes, you can say you have the first process, which involves 3 numbers or 3 digits, and then you add the result to the last part. Do you understand? Because there's no rule that tells you 1, 1, 1, 1, 4 ones, right? You get confused, I'm sure. I don't know if this is making sense here. So let's do this, right? What I would do if I were you is I would break it up into pieces, right? I create a sub-process, and then I'll say I'm going to evaluate, and I guess I'll just highlight this in a separate color here, maybe green or something. People like green, right? I don't know. Green because it's on the flag, I guess. So 1, 0, 0 is 1. 1, 1 is, and this is the thing here. In fact, what you're better off doing is breaking it up like so. Maybe into three. In this case, we'll probably have 3 different things, right? Because you don't want to confuse yourself. So it will be 1 and 0. This is the part where we use green now. It's 1 and 0, it's 1. 1 and 1. 1 and 1 is 0, remainder 1. 1, 1, 1, which is 3 ones, it's 1, remainder 1. 1, 1, 1, it's 1, remainder 1. 1, 1, it's 0, remainder 1. Right? We have this thing here. And then what we would do is we would get the intermediate result. We got the part that's in green, right? And then add it to the stuff that we got as a sub-process after multiplying. So effectively what we're doing, what I'm saying is we would add these things here together. Or maybe at this stage you could actually even add this, but it doesn't matter anyway. You can have 3 sub-processes if you want to. So observe, it would be 1 and 0, it's 1. 0 and 0, it's 0. 1 and 1 is 0, remainder 1. 1, 1, 1, it's 1, remainder 1. 1, 1, 1 is 0, remainder 1. 1, 1, 1, it's 1, remainder 1, right? So we have that. And then we will get this intermediate result again, and then just add the last result of multiplying the ones here, right? So we say 1 and nothing here is 1, 0 and nothing is 0, 0 and nothing is 0, 1 and 1 is 0, remainder 1. 0 and 1 and 1 is 0, remainder 1. 3 ones, it's 1, remainder 1. 3 ones is 1, remainder 1, right? And then we have this value here, which I hope does make sense, right? Because if you think about it, this is a 0 up to 1. So we have we need to add 2 to the power this. What we're effectively doing here is adding up. Hope we've done the right thing. I think we have. What we're doing is we're adding up 128 plus 64 plus 32 plus 1, right? So that we have 225. So the thing here, right, and I guess people are kind of confused. So what's happening here? I was trying to showcase a very peculiar case where, oh, no pun intended. I was trying to showcase a very strange scenario where you would have a lot more bits than what you know the rules to be, right? So question is, how do you add 1, 1, 1, and 1? What I'm saying is you view this type of problem as consisting of 2 parts, right? You start with the top part where you evaluate the 3 ones, and then you use the intermediate result to add the last bit here. It's simple. It's probably the cheapest trick in the book or something. But I'm sure you guys are smart. I'm sure you can easily form a mental picture and add maybe even 5 ones or something. Is this making sense?
Can you go over it one more time, sir?
Go over what? This example here.
No, the adding of 4 ones.
Okay. This is confusing. So observe, right? If you have 4, we know that the most complex case when you're adding numbers is a case where you have 3 ones, right? Remember these rules, right? Where we are saying the answer here is the answer is 1, and then we carry 1. This is the complex of all cases. The other cases are pretty trivial, right? The case where you have 1, 1, and then 2 zeros, 2 ones, and 1 0, and 3 zeros, right? Those are simple cases, but this is the most complex case. Now, the question to ask yourself is, what we're saying is, what then do we do when we have a situation where we have 4 ones that we need to add? And this is there when you're multiplying large numbers. Like here, we were multiplying a very large number, 15 times 15. So what do we do then? We're saying, because there's no rule here. Is there a rule that tells you what the answer is when you add 1, 1, 1, and 1? No, it's not there. Because it's not there, what you can do is you can break this thing up and just say, this is not, it's like Yeah, so you could say this is no longer, you can view this problem as being a 1 plus 1 plus 1, get the result, and then result plus 1 problem, right? So effectively what you would do in this case is you say, move this bit below, evaluate the sub result here. So 1, 1, 1, 1, 1, we use the same, anyway, I hope this is not confusing people here. But assuming this is the carry result. So what we're saying is 1, 1, 1, the remainder is 1, the answer is 1. Right? Because the remainder is 1 and there's nothing here, we move this 1 here. So in fact, the result is going to be 1, 1. And then we would add this to this. In which case here 1 and 1 gives us 0 remainder 1. 1 and 1 gives us another 0 remainder 1. So the answer would be that. So just be very careful when you're evaluating extremely large binary numbers, right? Where in situations where the rules don't apply anymore. All right, and it can get even worse, right? You can get worse. Imagine a situation where you're no longer dealing with a number that uses 4-bit representation, but you have a number that is represented using 5-bit representation, right? And if both numbers that you're evaluating are being done using 5-bit representation, it's going to be even more complex, right? Because what you'd have is a situation where you're saying, I guess I'm just going to have to do this here, yellow. Yellow is nice, right? I don't know, like a yellow lab or something. So 1 and 1, 1, 1, 1, 1, 1. And then you move here, 1, 1, 1, 1, 1. You move here, so here, 1, 1, 1, 1. You move here, 1, 1, 1, 1. Ooh. Right, 1. There's another 1 here. It's supposed to be a 1. You move here, 1, 1, 1, 1. This is what I'm saying here. Now you have, because remember, for you to get the answer, multiplying this times this.
The second last one has 4 digits.
Sorry?
The second last one has 4.
Oh, right. Sorry, I'm using 1, 2, 3, 4, 5. It's actually 2 of them actually that have 4 digits, I think. 4. 1, 2, 3, 4. Wait a minute. So 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Thank you. Great. So this is what we have, right? Because it's a large number here. So this is what we have. And so evaluating this would involve you adding up. Imagine a situation where you're adding here. In fact, once you start, if you decide to say you're going to add them, you're stubborn, right? So no, I will add them just the way I want to add them, right? This is addition here. This is going to be a bit complex, right? Why? 1, 1, and 0, 0, 0, 0, 0 here is probably going to be 0 something. If I can just make it green or something. This is 1. This is 0, remainder 1. Now already the problem has started because the carry bit here, the carry bit from here, 1 and 1 is 0. 1 and 0 is 1. 1 and 1 is 0, remainder 1. So we have 4 ones now. What are you going to do with the 4 ones? There's no rule that allows you to evaluate the 4 ones, which is why I'm saying you must break it up into pieces. It's like when you're working with decimal numbers, right? What's the easiest way of adding 5, 5, 5, 7, 3, right? If you can easily add these things together without a problem, but a smarter way is you start 5 plus 5, you get the intermediate result, and then you add this to 7 plus 3, right? This is the easiest, really. This is like 10 plus 10, which is 20, right? So this is what you need to start thinking about, right? How to break up the problems. It turns out that these problem-solving skills come back again once you start looking at computer programming in 2010, right? How do you solve problems by writing code, right? You need to think. You need to think logically. You need to think about how you can break up a problem into smaller manageable chunks. We also look at this once I don't know if we're going to gloss over that, but once you look at NIPS assembly as well, you notice that it becomes extremely useful for you to view a problem as being composed of smaller manageable pieces or chunks. All right. I hope this makes sense. Are people confused or something?
Sir, yes, I'm confused. Is there any other method that we can use to multiply the? Oh, is it adding? Yeah, adding the four ones.
Yes, memory. You can use the calculator. I'll show you just now.
Yeah.
1, 2, 3, 4, 5 times 1, 2, 3, 4, 5. And I'm joking. In the exam, there's no calculator, and then you get your 961 or something. Now, I'm just joking. I don't know of any method. So let me answer your question here. Probably not a very funny joke here, but I don't know if there's any other easier method of doing this. This is what I feel is the easiest way to multiply binary numbers because it comes naturally for you. It's the same method that was introduced to you in grade 1. You remember what Miss Banda taught you, right? How to multiply numbers here. I'm sorry, but maybe we can do a bit of research. I'm sure the math majors, have you looked at, are you looking at number systems? Have you looked at numbers that, do you know of any method that is much easier to work with when multiplying binary numbers besides what we're looking at here? And I know you're in here, the math majors, right?
I think that would be the easiest, the same method that we did.
Okay, maybe we can flip the question. Do you know of any other method?
No.
Okay, that's very strange. Are you sure you're doing maths or something? Anyway, is Mr. Chpeta or is it Dr. Banda teaching you? Dr. Banda taught me, very nice person, I suppose. Mr. Chpeta too also, but that was many, many years ago. Who's teaching you maths?
Dr. Kinkonko.
Yeah, never heard of her. Is it a her? I think it's a her, right?
Yes.
Yeah, never heard of it. Probably a new person. But anyway, it's neither here nor there. Also 13 years ago, much earlier actually. It's in 2000 and I was in NS in 2004 myself. Yeah, 2000. Yeah, 2003 I think. I don't know. No, when was that? I don't know. Yeah. So anyway, and I see 1743. I wanted us to immediately dive into binary division, but looking at the time, but we can, right? Nah, looking at the time, I don't want to confuse people anymore. Can I ask that you sleep over this, right? Just play around with, just try and see if you can understand the multiplication part. And then, actually what we can do on Sundays after the revision, we can look at some other problem sets so that we reinforce this. I think that's what we'll do on Sunday or something. One of those mixing tutorials we'll have or something. Very sad. Okay, but this is fine, right? Please get into the habit of learning how to use your calculator. You will need it in the final exam. You are allowed to use a calculator. You want to take advantage of the calculator to verify the final answer. You are told multiply these numbers. 1010 times 101. You should, because there are marks allocated to showing your working. Sometimes you lose marks if you don't show your working. You just get out your calculator, your scientific calculator, like what Lighton is doing here, and then you say 1010 times 101. Boom, you have your answer. In fact, you use your fancy calculator. Make sure you have that nice calculator to even verify the answer. What is it in decimal? It's 50. Okay. Is it really 50 if I multiply 1010? If I multiply 10 times 101, 10 times 5. Oh, yes, it is, right? Okay, I'll see you when you see me, which is day after tomorrow, I guess. We will wrap up binary division, and then I have a sneaking suspicion we shall actually dive into at least sign magnitude. That would be nice. So I'll see you on Friday morning, bright and early, right? Thank you very much. Good night, I suppose. Please think about, before you sleep, you must think about what you did in quiz number 12. That was very bad, right? The performance was really bad. You must look at yourself in the mirror and ask yourself why this is happening to you. Good night. Thank you.
Right,
Good
sir.
night.